the Fibonacci numbers grow, we see through this paradox that these numbers must be getting close together. But what, in fact, are they getting towards? That's the question. Well, to see that, what we should do is try to look at these things in a different way. So let's now actually return to the quotients, but look at the quotients in a different way. So in particular, let's return to the idea of how these numbers were generated by adding the two previous people to get the next one. And so in fact, let's actually take a look at the example and take a look at, say, 2 divided by 1. Well, we can actually rewrite that 2 on top as 1 plus 1. And if I do that, then I could actually write the fraction 2 over 1 as just 1 plus 1. Or if I wanted to, 1 plus 1 over 1. Well, that doesn't seem to be too useful, but you notice that all we see there are 1s. Let's move to the next one, 3 over 2. If we look at 3 over 2, and we write that out, the 3, we can express as 2 plus 1. And if we look at 2 plus 1 and divide it by 2, what do we see? What I see is 1 plus 1/2. Well, but 1/2 is precisely the reciprocal, or the flip, of what we just did, namely 2 over 1. So I could actually write 3 over 2 as 1 plus 1 over 1 plus 1 over 1. Well, that's sort of a mouthful, but you can sort of see it on the screen, and you can see that it's just a fraction within a fraction within a fraction. And in fact, if you keep trying this, you see the pattern continues. So in particular, if you take the quotient of 2 consecutive Fibonacci numbers, what you're going to see is a continued fraction, a fraction within fraction within fraction of 1 plus 1 over 1 plus 1 over 1 plus 1 over, and so forth until you get down to that last 1. This is an incredibly surprising discovery, and for mathematicians, this is an amazing breakthrough because now we're seeing some hidden structure that was by no means obvious or apparent by looking at how the Fibonacci numbers were defined. And yet we see that if we look at the quotients of any 2 consecutive ones, we can express them just as a long continued division of just the number 1. Again, fantastic structure. Well, in fact, this fantastic structure is sort of amazing because it's a defining trait. There are no other fractions except for quotients of Fibonacci numbers that have this feature of being expressed just in terms of 1. So it's a really, really special discovery. Now, how can we use that to lead us to the target of that number, 1.618? Well, all we have to do is take this to the extreme. As we continue to look at these quotients, what happens to these fractions? They're just getting longer and longer and longer. So we see 1 plus 1 over 1 plus 1 over 1 plus 1 over, and so forth. And if we were to see the target, we would just do this forever. And so we'd have this infinite list of 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 forever. And how can we figure out what that long, complicated looking number actually is? Well, there's actually a way of doing that, and here's what I want us to do. Imagine putting a frame around the inner 1 plus 1 over 1 plus 1 over 1, just as you see there. If you just look at that frame and look at it closely, you see it's nothing more than this, the original number again. For we just see this infinite long list of 1 plus 1 over 1 plus 1 over 1 forever. So if we call that original number, phi, the Greek letter phi, then in fact we see that the boxed in expression in fact is simply another copy of phi. And so from this infinitely long process, we can produce an actual closed algebraic equation. And the algebraic equation, which I'll just say, is phi equals 1 plus 1 over itself, or phi equals 1 plus 1 over phi. And now we can actually use algebra to solve that. In fact, if you are a fan of the quadratic formula, you can actually solve it. And you'll see that you get 2 answers, and we're looking for the positive one. And so we discover that phi is the number 1 plus the square root of 5, all divided by 2. Now that seems like sort of a strange, weird number, but all we have to do, in fact, is look at that number on a calculator. If we type in 5 and hit the square root key and then add 1 and then take the whole thing and divide by 2, what would you see? You would see 1.618033989 and so forth. We see again the decimal that these fractions were heading toward. But now we can express that infinitely long collection of 1's in a very, very tight expression. Just 1 plus square root of 5 over 2. And this is a wonderful thing that mathematicians love to do. Mathematicians love to take something that sort of is unwieldy, but somehow natural, and see if they can re-express it in a different way. In this case, we have this wonderful, beautiful expression of just a long list of 1's being divided by itself, which is quite pretty and I would argue aesthetic in its own right. And what we're doing is we're bringing some mathematical principles into play, and we see that that infinite process can be expressed in sort of a finite statement. But that finite statement costs something. There's no such thing as a mathematical free lunch. If you have an infinitely long, complicated sort of thing of 1's, then if you're going to rewrite it in a different way, that rewritten expression should be complicated as well. And in this case, we see that sort of square root, that threatening square root symbol there. But it turns out we're able to actually produce this very, very tight expression for this wonderful, beautiful run of 1's dividing, dividing, dividing. So we have this number 1 plus the square root of 5 over 2, which we've already seen in its decimal form can be expressed as 1.61803398, and it goes on forever. This number, in fact, is called the golden ratio. And it's an extremely famous number, and I must editorialize, if you'll allow me. My research interests in mathematics are actually in number theory. Are in precisely the kind of questions that Mike and I have been talking about so far in these lectures. Although I'm trying to prove theorems that have yet to be proven, so I'm trying to discover new truths. But a lot of times people see me on the street, they find out I do number theory, and they say, gee, Ed, well, what's your favorite number? Thinking that this they can use to gamble on or to play on the roulette wheel or so forth. And I tell them, it's not 7, it's not 3. It's 1 plus the square root of 5 over 2. It's this golden ratio. Now, why is it my favorite number? Well, first of all, because it's the only number that can be expressed in this infinite process of quotients, dividing, 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 just using 1's. Just using 1's. And as a number theorist, I find that exceptionally beautiful. But actually, I'm foreshadowing what we're going to be doing in our next lecture, where we're actually going to be looking at geometry and art, and actually think about the idea of aesthetics. And the question is, maybe mathematics and aesthetics somehow go together. And we'll see an interface through this golden ratio. So in fact, as this lecture is the last lecture where we focus on number, we're going to be moving to the next realm where we're going to think about the geometric visual world. So that's an excitement, little enticement that I want to plant in the back of our heads right now. This golden ratio, which is my favorite number, I hope to entice you with in the next 2 lectures in geometry and have you see that, in fact, it's potentially a candidate for your favorite number. Well, we have this number 1 plus the square root of 5 over 2, which maybe you don't like the sound of, so maybe the decimal is better, 1.61803339, and so forth. But in any case, we have this special number, the number that, in fact, these quotients of Fibonacci numbers want to move to. They're drawn. The quotients are drawn to this particular number. And that's sort of amazing. Well, I want to now close by returning to the Lucca numbers. Now remember, those are the numbers that have the exact same process as the Fibonacci numbers. The generating process is the same. We just take the 2 previous people and add them to get the next person on our list. The only difference is the starting seeds. Instead of starting with 1, 1 to generate and build the Fibonacci numbers, here Lucca started with the number 2, 1. And by adding those 2, we got 3. And then adding 1 and 3, we got 4. And we produced the Lucca sequence of numbers, which is 2, 1, 3, 4, 7, 11, 18, 29, and so forth that we saw in the last lecture. And you might recall that at the very end of the last lecture, I raised the question that even though those numbers don't agree, namely the Lucca sequence and the Fibonacci sequence differ after the first few numbers, is there any common structure given that, in fact, the generating process is the same? Well, now we know exactly how to look at this. We simply look at the quotients and see how they're growing. So when we do that with the Lucas numbers, let's see what happens. If we take 1 and divide it by 2, we see 0.5. If we take 3 and divide it by 1, we see the number 3. So far we go from 0.5 to 3. That's sort of wildly changing in number size. But then 4 divided by 3 is 1.333 forever. 7 divided by 4 is 1.75 So again, we're fluctuating a little bit. 11 divided by 7 is 1.571. 18 divided by 11 is 1.6363 forever. 29 divided by 18 is 1.61111. Notice what's happening. We seem to be actually heading toward the 1.618033, so forth. Let's go down a little bit further, and you see if we jump down to 123 divided by 76, we see 1.61842110. And all of a sudden we say, wait a minute, maybe, in fact, the Luca sequence is conforming as you do it longer and longer and compare the relative sizes by taking the quotients of consecutive Lucas numbers. Maybe, in fact, they're heading toward this golden ratio, Ed's favorite number. Well, in fact,